because the thing I want to cover this classical Lie group because while studying symmetric space, we need to really cook up examples, and examples are formed out of this classical Lie group. Precisely, these are some homogeneous spaces of some classical Lie group. So let me start that topic. By the way, I just want to tell that this RSS, this means this Riemannian symmetric space. Okay, this is not really the thing is which you think that Rashtriya Swayam or so. This is Riemannian symmetry. So Pritham, start the recording.
Yeah, I have started. You can start.
Oh, you have started. Okay. Yeah. So today I want to discuss some important topic, something called complex structure and complexification, and this is a very important concept. Okay, so definition. Let here be a real vector space. That is means vector space over R. A R linear map J from here to here is called a complex structure on here if J square is equal to minus identity. Okay. Observation. Suppose J here to here is a complex structure. Actually, VR is a real vector space. Okay. For that reason, I have really written that V superscript R. So that means J square is equal to minus identity. Now, if you put determinant in both sides, you will get determinant of J square is equal to determinant of minus identity. Now, determinant of minus identity, this will be minus 1 to the power dimension of VR over R. Okay. Now, since observe that left hand side is a positive quantity, this implies dimension of VR over R is even. Okay. So we want to discuss why this complex structure is important, so that discussion. Okay, sorry. Let V be a vector space over C. Certainly, B is also a vector space over R. Okay, to distinguish that, I really denote it by VR. So B also has a real vector space structure over R. Okay, just you just wait one. Okay, shit. Prit, just wait 1 second. Okay.
Yeah, sure.
Okay, so V also has a real vector space structure over R. So I call it VR, just to differentiate with the complex vector space structure. Okay, so set theoretically V is equal to VR. Okay. So first thing, observe that dimension of VR over R is equal to 2 times dimension of B over C. Second thing, you observe that consider this map J from VR to VR.
Munada,
Yeah.
you are scrolling too fast.
Okay, J from VR to VR.
Make it little slow.
This is okay.
Yeah.
Okay, J from VR to VR. This JB is equal to I times B. Okay, this is nothing but multiplication by I. One checks that J is one checks that J is a R linear map. And J square is equal to minus identity. This checking this J square is minus identity. This is EG for J square of B. This J of JB. So JA of JB is nothing but I times B, and J of IB, I into IB. This is called minus square minus B. So what I am getting this J is a complex structure on B here. Okay. Now second thing, suppose T belongs to T is a complex linear map on the vector space B. This implies T is certainly a real linear on B here. Okay. Now since T is complex linear, then that will respect the scalar multiplication with respect to I. Okay. Now, if you IB is nothing but JB, so I write T of JB, J of T times B. Okay. This is nothing but Tj is equal to JT. So what I am getting, T is a complex linear map on B, vector space B. Then T is a real linear map on B here, and Tj is equal to JT, and this is nothing but this is equivalent to saying that T respects the scalar multiplication with respect to I. Conversely, you can check that if T is a R linear map on B here, and T respects this scalar multiplication with I, then that means T is complex linear. So here I get if and only.
Yeah, Muna, can you repeat? Your first statement was that T is T respect
T is a
scalar multiplication by I. That is obvious, right? Because T is complex linear.
That is obvious, right? So
yeah.
T, that is
what
I
was
am
the
getting
other statement?
Other sentence. Suppose T is a real linear map on B here, and T respects scalar multiplication by I. That means T is a complex linear. T respects scalar multiplication with respect to complex number. That's all. So I am getting if and only if statement. Okay. So what I am getting, endomorphism of B or C. This is nothing but T belongs to T is a real linear map on BR such that Tj is equal to Jt. This is a very important characterization. Okay. So I am characterizing linear maps, C linear maps on B via this R linear maps on BR, which commutes with this complex structure J. Okay. Now fourth.
Sorry, Muna, actually because of some network issue, I missed the previous thing. How do you define complex structure on V?
Okay, VR. See, the thing is,
Yeah.
B is a complex vector space that
Okay,
has a real vector space structure that I am calling VR. just the different notation.
Okay, so
Say
it
theoretically,
already has a complex. Okay.
already a
I
complex
thought
vector
you
space
are
over C.
making it into. Okay.
It is also
Then you are defining J to be like that.
J is scalar multiplication by I.
Okay.
If you take JB is equal to IB, okay, is this clear?
No, I mean, actually, could you elaborate? What do you mean by color multiplication?
Okay, let me say from the beginning. So V is a complex vector over C, right?
Yeah.
So do you agree that it is a real vector space?
Yes.
So that space I am denoting by BR just to differentiate that from complex vector space structure. I am calling B is equal to BR. So set theoretically B is equal to BR. Okay. Now on BR there is scalar multiplication by I is well defined because it is already a complex vector space. So I define this map JB is equal to IV.
Okay.
So J is an R linear map and J square is equal to minus identity. Okay. So J is a complex structure on here. Do you agree with this?
Yeah, that's okay.
That's shocking. So next thing I am saying that suppose T is a complex linear map on B.
This one I could attend. Yeah, this is okay.
This is okay, right? So fourth point GLCB. By definition, this is actually all invertible complex linear maps on B. This is by definition T belongs to B such that T is invertible. Okay. So that is same thing you can write. T belongs to T is a complex linear, so that kernel of T is equal to 0, right? From the third point, actually, we have a characterization of complex linear map on B. From the third point, you can write that T belongs to here, so that Tj is equal to Jt and kernel of T is equal to 0, right? Now, look at these two things. That belongs to, that will implies T belongs to GLR VR, so that Tj is equal to Jt. Okay. So I will get here GLCB is equal to T belongs to GLR VR, so that Tj is equal to Jt. Okay. So third, in conclusion, so okay, is it clear? Is clear, Jyoti?
Yeah.
Okay. Now suppose I ask this question. Suppose VR is a real vector space. Can we give a complex vector space structure on VR? Okay. So it is the converse question. We are asking that VR is a real vector space, and can we make VR is a as a complex vector space? So if we can make VR as a complex vector space, then we should we will be able to define the scalar multiplication by I, and scalar multiplication by I is a complex structure. So then and answer is yes, if we can, if VR has a complex structure on it. Okay. Suppose Suppose assume J from VR to VR is a complex structure. We define let lambda belongs to lambda is equal to alpha plus I beta belongs to C. Okay, so I define this alpha plus I beta on V belongs to VR by alpha plus beta J applied on V. So VR, remember VR has a real vector space structure, but to make it a complex vector space, you need to.
But how you have a real vector space and you want to make it a complex vector space, right?
Okay. Yes.
But so you have to give some complex structure, right? You cannot assume
Yeah. No, I am saying that if suppose J from here to here has a complex structure,
that. Okay.
then I can give a complex vector space structure on it.
Okay.
Suppose
But you have to somehow ensure that also that it has a complex
I am
structure,
not saying
right?
that I am not saying that any real vector space has a complex structure. For
Okay.
instance, take you odd dimensional real vector space, then it will not have a complex structure,
Yeah.
right?
Yeah.
So I am saying suppose J VR to VR is a complex structure.
Okay.
Then I
Okay.
can define a scalar multiplication, and I am defining it how. That is what I am saying.
Okay. Fine. Carry on.
Is it clear?
Yeah.
So I am defining alpha plus I beta into V is equal to alpha plus beta J applied on V. Okay. Check that with scalar multiplication. Defined above, here becomes a complex vector space. I will call okay, VR becomes a complex vector space. We call that vector space VR tilde. We will stick to the notation. VR tilde means the complex vector space. So in this case also, say theoretically, V is equal to say theoretical VR tilde is equal to VR, but this is a real vector space, but this is a complex vector space. Okay. So now similar observations you can get dimension of on VR. You will get 2 times dimension of VR tilde over C. Second thing you will get that endomorphism of C on VR tilde. This is same thing as T belongs to T is a real linear map on VR. So T is really linear, and T should respect this multiplication by the I. That is, but multiplication by I is given by the map J. So Tj is equal to Jt. Okay. So second thing I hope is clear to everybody. Okay. So GLC VR tilde, I will get this T belongs to GLR VR, so that Tj is equal to Jt. This is a very these 3 observations are very important observation. Okay. So first thing I am saying, dimension of VR over R is 2 times dimension of VR tilde over C, and complex linear maps on VR tilde is equal to the space of all real linear maps on VR, so that Tj is equal to Jt. And third thing is invertible complex linear maps on VR tilde is real linear maps on VR which commutes with the matrix J, and it has to be invertible. So now let us give an important. This is a very important example. So let B is equal to Cn. Okay. Now the thing is, Cn is a complex vector space. You know. So VR set theoretically it is also Cn. Okay. But what I will do, I will identify Cn with R2n. Okay. And I will give the complex structure on R2n, and I will describe the linear maps or complex linear maps on Cn in terms of real linear maps of R2n. Okay, so this is the thing, and always in the process we will keep track of this identification, how Cn is really identified with R2n. That's all. So let Z belongs to Cn. Okay, so that means like Z is equal to something like x1 plus II1, x2 plus II2, x3 plus I3, dot, xn plus II1. Okay. So xi, yi belongs to R. Now I can write this as x1, x2, xn plus I into y1, y2, yn. I can write this as x plus iy, where x is equal to x1 plus x2, xn, and y is equal to y1, y2, yn. Yes, so I am right. So I am right. What I get, z is equal to x plus iiy, where x belongs to Rn, y belongs to Rn. So I will identify this z, x plus iy, z to xy belongs to R to n. This is same thing as Rn plus Rn. Okay. Now the scalar multiplication by I know that on Cn, the scalar multiplication by I is the complex structure. So I need to see what it translates to R2n. I into x plus iy, this is nothing but minus y plus ix. With this identification, if you look at this j from Rn cross Rn, so you will get that j of xy is equal to minus of yx, and this is with this identification. If you look at that j of xy is equal to minus of yx is our complex structure. Check that. Okay, so this is trivial. So j square is equal to minus identity, and this j is the complex structure on R2n. Okay. Now see, we have we have derived this thing, endomorphism of C over V is nothing but T belongs to endomorphism of R on VR. Okay, so that Tj is equal to Jt. Now, and also I have got this GLCV is equal to T belongs to GLR VR, so that Tj is equal to Jt. We have seen this in the beginning. Now here Cv is equal to Cn, and VR actually with this identification, this is actually R2n. There is some identification is going on Cn with R2n, and J is the corresponding this complex structure. So here you will get that if you put this and what are the complex linear maps on Cn over C? That is nothing but if you will put this thing, you'll get MNC. Okay, this T belongs to M to n R, so that Tj is equal to Jt. And you will get GLNC. If we will put this, T belongs to GL to NR, so that Tj is equal to Jt. Okay.
Munna,
So it's yes, sir.
maybe you can write down the matrix for J.
I will write, sir. I will describe everything. Actually, I will describe the embedding. Okay. So this MNC and GLNC, J has a matrix representation. I will describe everything. So this from this is a very important equation. From this you will get that MNC is a closed subspace of M to NR from this description, and you will get that from this description GLNC is a closed subgroup of GL to NR. Okay, this is clear because this is given by some equation. Now actually here what I am getting, okay, look at this expression. This MNC sits inside M2NR. We are getting an embedding of MNC inside M2NR, 2n cross 2n matrices. Okay, so MNC sits inside Mn2NR. So I want to look. So suppose I call this Z. Okay, so this mapping I am calling Z. So suppose let T belongs to MNC. Now T you can write it as A plus IB, where A belongs to MNR. Okay, A comma B belongs to MNR. Okay. I want to see that how this ZT, what is ZT basically? I want to look. Okay, this is my question. So remember, this is to determine what is the ZT. Remember this, I have to really. I want to see how this action, what is the action of A plus by IB on some specific element on Cn. Okay, so let okay, sorry. Okay, so let x plus Iy belongs to Cn, x belongs to Rn, y belongs to Rn. Okay, so A plus IB, if you will act on this thing, and x plus Iy, you will get what? Just multiply Ax minus by plus I into bx plus ay, right? So z of A plus IB. Okay. So what is this map? This will, if you remember the identification of Cn with R2n. So z of I plus B, this map will send the xy to, this is something like Ax minus by, bx plus ay. Okay. So that means this will, let us write down this thing, column thing. Xy will go to A minus B, BA. Is it clear? Manoj, is it clear?
Yeah. Thank you.
So Z of A plus IB is this matrix A minus B, BA. Okay. This is the embedding. So Z of I plus B will look like A minus B, BA. Okay. Now what is J? J is from Rn cross Rn to Rn cross Rn given by J of xy is equal to minus yx, right? Now this is if you look at this matrix representation, actually on R2n we are taking standard basis, and Cn also we are taking always standard basis. Okay, so matrix representation of J will be something like 0 minus, okay, 0I minus I0. Okay, if you look at this thing, that 0I minus I0. Okay, where I is a I is the n cross n matrix. Okay, I is, yeah. Okay, so there it goes. Okay, that's okay. Now I have given this thing. This I have again written that T belongs to MNC. MNC is something like T belongs to M to NR. Okay, so that Tj is equal to Jp. Okay. So now the thing is, suppose let T belongs to M to NR. Okay. That means T is of the form A, B, C, D. Okay, A, B, C, comma D. This belongs to MNR. Let us see what is this condition Tj is equal to Jt translates. So Tj, suppose Tj is equal to Jt. So A, B, C, D, 0 minus I0. Okay, so 0 minus I0, A, B, C, D. Okay, so that will give you C minus A, B, this is minus B, B minus B, minus D, A, C. So if you look at this line, this thing, third line, so we will get that D is equal to A and B is equal to minus C. So T has the form. So if you will substitute that, okay, so recall that T is equal to ABCD. So T has the form A, B, C is equal to minus B. So minus B, D is equal to A. Okay. So T is of the form Z of A plus I. So I can write this sign like that. MNC, sorry, MNC is equal to A minus B, B, A. So that AB belongs to MNR. Okay. Similarly, I can write this M. If you really GLNC A minus B, B, A. So that this matrix A minus BA is invertible, and AB belongs to M. Okay, so this is a very important thing. Which, okay, so now let us okay, this is the thing. So here actually, what is the basis of Cn? Basis of in this thing actually, Cn over C is our this standard basis is suppose U1, E2, En. Now what is?
Muna, hello, Muna.
Yes, sir. Yes, ma'am.
This super Nair. Yeah. So
Yeah.
this GLNC's definition was something with GLNR, right? So what happened
Oh,
here?
Actually, I am giving here GLNC. I am giving the expression of GLNC in terms of GL2N.
Okay.
2NR. For that reason, actually, I am getting this. GLNC, all are real matrix. A belongs to MNR. Yeah. So that this matrix is involved. All I am saying that this matrix is of this part. Is it clear?
Not really. The thing is, what is the difference between the two sides, left hand side and right hand side? It's in this real form. It is like this. Is it?
It's an
No,
embedding
I am
inside GL2NR.
2N to NR. That's all.
So you don't have. So ABs are generally from MNR and not GL.
AB belongs to MNR.
AB belongs to MNR such that A minus B, B, A, this is in GL2NR, right?
Yeah, GL to NR. Okay, I should have written that GL to NR. This is better.
Yes, okay, fine. It's okay. Sorry. This was a very trivial question. Yeah, fine, okay. Fine.
Okay, so what is basis of Cn over C? We are really, this is E1, I2, In. Okay, basis of R2n, what I am getting here. These are also standard basis, but I am writing this is in terms of F1, F2, Fn plus 1 up to F2n. Okay, so now because I am using different symbol because it has n coordinates and it has 2n coordinates. Simply for that reason I am writing. Okay, so now F1 is nothing but if you really E1 0. Okay? So Fi is nothing but your EIE 0. Okay? 0 is in Rn. If you so F1 is E1 belongs to Rn and 0 belongs to Rn. Okay, so Fi is EI 0. So F1 is, so here I is 1 less than equal to n. Okay, you observe this Fn plus 1. This is nothing but J of F1. See, we recall this J of xy is equal to minus yx. So what I'm saying that Fn plus 1 is equal to J of F1. Is it clear? Pritham, is it clear? J of F1 what is? So J of F1 is equal to J of E1 0, right? So that will be, if you put this J of xy is equal to minus 2yx, so J 0 of, okay, sorry, 0 U1. So that means at n plus 1 place, it is 1. This is F1 plus 1. Similarly, you will get J of Fi is equal to Fn plus I, where I belongs to 1. So I will write this basis of R2n something like some in a different language. Basis of R2n is something like F1, F2, Fn. Okay. So J.
So what are you trying to do here?
I am just writing this basis in a different form because I have a purpose.
Now after that, what is your goal? What do you want to do with that?
Okay, I will do. Okay, I will write.
Okay.
So I am
Okay,
saying
fine.
that I am just F1 plus F2n. I am saying that if A plus IB, okay, belongs to MNC, okay, it has matrix representation like A plus IB on R2n. On R2n, okay, and if you take this basis F1, F2, Fn, JF1, JF2, JFn, then it has representation like A minus B, BA. This is clear, Manoj?
I think so.
See, the thing is,
Yes.
A plus on A plus IB, suppose this is a linear map in Cn, okay. So on this basis, standard basis, it has representation A plus IB. on R2n, if I am taking this basis F1, F2, Fn, JF1, JF2, JFn, then I have this matrix representation A minus B, BA, right? This is just saying things in a very different language. A plus IB, let us call this B tilde. A plus IB, B tilde. Saying things in a different way just. Okay, so I want to give an exercise now. Exercise, let V R be a real vector space with a complex structure structure J from here to here. So I can let us say, so let V be the corresponding complex vector space. So let B, okay, let script be W1 is right.
Can you just go back to the last line?
I am saying that suppose
Yeah.
VR is a real vector space. Exercise is something like that. That VR be a real vector space with a complex structure J from VR to VR. Okay, so we can make it a complex vector space, and I am calling that V. Okay, so I am saying that suppose W1, W2, Wn is a basis of V over C. Then so that this set W1, W2, Wn, J of W1, J of W2, J of Wn, this is a basis of VR over R. Okay. Now let T belongs to C, V, and suppose T is a complex nonlinear map on B over C, and T has this matrix representation with respect to B is like A plus IB. Then T has matrix representation with respect to B tilde, something like A minus B, B. Is it clear now? This exercise is clear. This
Yes,
is a very
yes,
simple.
yes.
For that reason, I was writing this standard basis of R2n in JF1, JF2, JFn. Okay, so this is a very simple exercise, and you can do it. If you can't do it, then tell me in the message. This is very simple exercise. Okay, now I want to.
No, this is like both the vector spaces will be isomorphic to Cn and R2n, right?
Okay, something like, okay, you do on your own. Okay, so. So now I want to discuss some very important thing, this complexification. Okay, of a real vector space. So this is a very, actually I will, the previous example is a very important example. So I want to really mimic the same construction on, so in the abstract setup. So let So let W be a real vector space. Just I am right vector space, that is vector space over R. I am not writing WR because the notation will be cumbersome. Okay, I am not writing WR. Just to remember that W is a real vector space. Okay. So then this implies W cross W is also a real vector space. Okay, this is trivial. Now in case of Rn, J in cross of matlab Rn cross R2n, this complex structure is like J of xy is equal to minus of yx. Okay. I want to follow this idea, so I define J from W cross W to W cross W by J of say UV is equal to minus VU. Okay, so check that J is a complex structure on W cross W. Okay, now so this is the same thing. The J of U is V is minus VU. Okay, so W cross W can be made a complex vector space. We call that vector space WC. We call that vector space complexification of W space. Sorry. W, it is denoted by WC. Precisely, WC is nothing but this is the W cross W tilde. This is the tilde is the notation for corresponding complex structure, a complex vector space structure. Okay, and we call W as the real form of WC. Now, W has an embedding inside.
Munna, just curious question. So you are considering only finite dimensional vector space here, or you are considering
Only
infinite
finite
dimensional
dimensional spaces.
Only
Only
finite
finite.
dimensional.
So W has an embedding inside WC by this W going to W0. Okay. So let W belongs to WC. Said theoretically, this WC is nothing but W plus W. Set WC is equal to W plus W, said theoretically, right? So I write W is equal to UV. Okay. U belongs to W, V belongs to W. Okay. Now I can write that U0 plus 0V. Okay. Now U0 and okay, so J of V0 is nothing but your 0 of 0V. Remember this J of xy is equal to minus yx. From there I am getting that J of V0 is equal to 0V. So I am writing that J of V0. Okay. So this with this identification of thing, I will use this identification. So this belongs to W, this belongs to W. So I will get U, but this action of J is nothing but the scalar multiplication by I. So W is equal to U plus IB. Okay. So what I am getting? And this representation is any element W belongs to WC can be uniquely written as W is equal to U plus IB, where U belongs to W, B belongs to W. Okay. So now the thing is, with this writing, I can check that A plus IB. Okay, this color multiplication, something like the usual thing, A plus, like the usual way. Okay, this is not okay. You can, okay, but you will write this is like AU minus BB plus I into BU plus AB. UB W AB belongs to R. Okay. So what I am getting, any element W plus WC can be uniquely written as W is equal to U plus IB, where U belongs to W, B belongs to W. This is the very thing. This is all about. This is what I wanted to tell about the complexification, but it has another description, and that is also useful by algebraists. And you should really. I am just saying what is that another by algebraist. So these two things are important actually. So you take. So what I am giving now, this I am given one description of complexification, and I want to give another description of by algebraist. Okay. So let W be a real vector space. Okay. Now I take this WC. I define like this. This is W tensor C over R. Now I take a simple element. Take a simple element. Take suppose W tensor lambda take belongs to WC, okay, and alpha belongs to C. So I define this thing alpha into W tensor lambda. This is W tensor alpha lambda. Okay. With this scalar multiplication defined like this, check that WC is a complex vector space. Okay. Now so WC is a complex vector space. Now here also I have an embedding of W inside WC. So you will get the embedding is like that. W you will send to W tensor 1. Okay. Now you take a simple element W tensor lambda, where lambda is equal to say alpha plus I beta belongs to C, alpha beta belongs to R. Okay. So W tensor lambda you write like W tensor alpha plus I beta. Okay. So what you do, you take W tensor alpha plus I, just use the tensorial property tensor beta. So you will get alpha W tensor 1 plus I into beta W tensor 1. See, look at the embedding. I have the embedding W going to W tensor 1. This with this identification, this alpha W tensor 1, this belongs to really your W. This belongs to W. With some work you have to do. This I have done for simple tensor, and any element of WC is a linear sum of this W tensor lambda. So after that you will get that in this case also we will see that we will get that any element W belongs to WC can be uniquely written as W is equal to U plus IV. U belongs to W, V belongs to W. Okay, this is a very important thing, and it will also characterize the complexification. So let me give an exercise to you, all of you. Exercise. Let V be a complex vector space and W be a real subspace of V such that every element V, okay, every element V belongs to V can be uniquely written as V is equal to W1 plus IW2. W1, W2 belongs to W. Then so that V is equal to W complication, WC. This is a easier trivial exercise. Okay, if you now examples are very so this is the exercise. So this exercise is very useful. Right? So let me read it once more. Let V be a complex vector space and W be a real subspace of V, so that every element V belongs to V can be uniquely written as V is equal to W1 plus IW2, as then so that V is equal to W. V is isomorphic to, right? And this thing as uniquely written is a very important thing. Okay, so and example, one thing is, you know that I have already discussed RNC is, this is Cn, complexification of Rn is Cn, so Rn is a real form of Cn. Okay. Now second thing, you know that every element
the form word you are using in what sense here?
If something like W is a vector, real vector space, so W actually WC is called complexification of W, right?
Yes.
And W is called real form of WC.
Okay.
If you understand,
But what I am saying is it does not contain any other meaning, right? It's just a real form you want
actually
to
we
say.
will define this thing in terms of Lie algebra. So actually I am doing for vector space, then there you will have some meaning.
Okay. Okay.
MNC, any element of matrix MNC can be written as this uniquely in terms of, okay, if T belongs to MNC, then T can be written as uniquely that A plus IV, where AB belongs to MNR. Okay. So that means MNC is nothing but complexification of MNR, and MNC or MNR is a real form of. There can be many real forms of a given complex vector space. So, but we will, it is not important at this moment, but we'll come back to it when we prove the duality between compact and non-compact symmetric space. So this is all about complexification and the complex structure. This is a very important concept, so we'll come back to it. So now actually,
Munna, I just have one question.
yeah.
So when in the identification of these MNC with the M2 and R with that commuting property, they're also called symplectic matrices, right?
Actually, this No, actually, we will prove something. Okay, don't worry. There is something. Okay, some connection is there, but not here. Now, don't worry about this. We'll see various things. Okay, it has the connection with some symplectic things. Okay. This is actually this J actually J in a sense that you will get that if you take symplectic group and you take that corresponding matrix, uh, it will be sub minus of that actually. Minus J will be the corresponding matrix which will correspond to this symplectic group sp2nr. Okay, so we will give we will prove many results. Okay, so
Now, I think what you're saying is, I understood that the set, the MNC is the set inside M2 and R, preserving some symplectic form.
that will not exactly be that symplectic form.
Okay.
Okay, I have to check.
Was this
it,
that
okay.
this question or?
Yeah, actually, yes, it was not, the question is not entirely correct. Yeah, I think I mixed two things here. Yeah, so what Munna is saying is, yes, those complex forms, what did you say? Complex structures, they come from symplectic matrices in general.
Yeah, it
Yes.
has.
Okay,
So
hi. Yeah, I
because
think
of
that
that,
is,
we will get various
yeah.
interesting relations of between
Are you talking about the connection of UN with SO2N with this?
yeah. I will talk those things.
Right?
Okay.
Yeah.
So all those things I will talk, uh, but these are after few classes. Okay. So this is all about complexification. I have 3-4 minutes. So let us define one thing, then I will stop them. So actually I will talk about classical Lie groups. Okay, so classical Lie groups, actually these are basically groups which preserves certain bilinear form or sesquilinear form over R, C or H. But we will discuss something little more general thing, something called matrix Lie group. Okay, so matrix Lie group. Okay, observe. Okay, so let me use a phase space. The matrix Lie group. Okay, so first observe that GLNR is a closed subgroup of GLNC. This is a trivial. Now we have seen that GLNC is nothing but T belongs to GL2NR, so that Pj is equal to Jt. Now, so that implies GLNC is a closed subgroup of GL2NR. Okay. Now what I am getting, GLNC is a closed subgroup of GL2NR. So here is the definition. So a group G is called a matrix Lie group if G is a closed subgroup of GLNC for some n. So n belongs to n is positive into the n plus. Okay, since GLNC is also a closed subgroup of GL2NR, so what I will get? I will get that equivalently G is a matrix Lie group if G is a closed subgroup of GL and R. For some n. Okay, so since actually the thing is since GLNC is a closed subgroup of GL2NR and GLNR is a closed subgroup of GLNC, so these two things are really equivalent. So just however, we will use this first definition always. Okay, so there is a theorem which is I will take 1 or 2, at most 2 minutes. Okay, just okay, at most 2 to 3 minutes. Okay, so the thing is there is a theorem which called Carter's theorem. So that we say that if G is a Lie group and H is a closed subgroup of that, then H is also a Lie group. You can put a differentiable structure on H, and therefore H is also a Lie group. So this implies matrix Lie groups are Lie groups. Lie groups are Lie groups. So one can define a Lie algebra in that thing. So this it's Lie algebra G is equal to, okay, so X belongs to MNC, so that e to the power Tx belongs to GL. Okay, e to the power Tx belongs to G for all T belongs to R. Okay, now here
Yeah, there you meant, sorry, there you meant that matrix groups are Lie groups, right? What do you mean?
Yeah.
Matrix Lie groups are Lie groups.
by Cartan's theorem.
Yeah. Okay, we are defining matrix Lie group to be a closed subgroup of.
So,
okay.
So examples of this matrix Lie groups are like something. Okay, GLNC, SLNC. Okay, so GLNR, SLNR, GLNR cross. Okay. UN, SUN, ON, SON, etc. Okay. It is really customary in this Lie theory that you write these groups in capital letter and Lie algebras in small letter. So Lie algebra of GLNC, you write in this something like small GLNC. So Lie algebra of suppose SON, you write in small letter SON. Okay. So exercise.
So you are treating them as real Lie group, right?
Real Lie group. Everything is real Lie group.
Real group.
Exercise. Find Lie algebras of all groups familiar to you. This is a very easier exercise. Okay, so
Mona,
I will not really prove this exercise, but you
I
can.
ask
Yes, sir.
I mean, you have told us what is a matrix Lie group, what is a Lie group. You didn't tell us what is a real Lie group because somebody was asking it. That's why I asked.
Lie group means real Lie
No,
group.
since you are saying real Lie group, one suspects that there is something called complex Lie group, but that you didn't define. That's why I'm asking.
If that see this Lie algebra, okay, I have not defined this. If this Lie algebra is a complex vector space, then it is called complex Lie group. Is it the definition? Actually, this is the definition which I see. The thing is, okay. Okay, so I am saying that. Okay, let me give the exercise first. For instance, GLNC is MNC.
No, when we say a real Lie group or a complex Lie group, does it have to do with the complex manifold or something like that?
Okay, just wait. Shall I? So I actually precisely have not checked this thing, that what is the definition of complex Lie group, but the definition which in my mind is this thing. Suppose definition of, I will check it. Okay, so it might be wrong. Definition of a complex Lie group. So if you take this, suppose G is a Lie group.
No, Munna, you have to define a Lie group first.
Actually,
Did you define the Lie group or not? I haven't seen that.
Okay, yes, and defined.
okay, I have not defined, but I thought that I will not define. Okay, next class, then I will define the Lie group. Actually, I was thinking that Lie group, Lie algebra, I will not define.
Mona,
Yes, sir.
I mean, let's get it straight. You want to talk only about something called matrix Lie groups. There doesn't exist anything called Lie groups. That is your line of action. Then we will go by that. I mean, what is a Lie group and all that doesn't make any sense. Only matrix Lie group makes sense according to the notions which you have defined. You want us to go by that? That is fine. But I think people are having
I will
confusion
go by that.
perhaps.
No,
Or the-
but still there you need a differential structure, right? So my question was precisely, suppose you are taking SL and C. So what structure are you using? So are you using the real structure or complex analytic structure? So I think he's going to, what he answered, I could understand that he is going to use only the real manifold structure there.
No, let me clear something actually for that reason first. First, actually, I will. The thing is, first few lectures, actually, you will not really need much about this abstract Lie theory. Okay. So if you are in matrix Lie group thing, then you will be very, you can easily do things. But the thing is, for latter thing, I really need this so-called Lie theory. Okay, some preliminary of Lie theory. But I was thinking to not to skip those things because it will take some time. Okay, but now it seems that I have to define that.
Okay,
so
I mean,
that
let me just interpret. I mean, if I have created some confusion, since somebody asked, that's why I said, I believe you want us to work with something called matrix Lie groups, which you have defined. There is nothing called real Lie group, complex Lie group for the time being. It's only matrix Lie groups.
Yes, sir.
And everything makes sense.
Okay. And then another thing actually, which you people, since he has asked this question, actually there is something. See, the thing is, okay. See the definition of Lie group I am giving. Because I am taking some time. Will it be okay, or I will leave that now? Pritam, will you continue
Yeah,
little
sure,
more?
sure.
Okay, so I am giving this definition of Lie group. It's just let G be a smooth manifold. Okay. G is called a Lie group. So if this multiplication map xy, see this M, first thing, this okay, xy going to xy inverse is a smooth, if is a smooth map from G cross G to G. This is the definition of Lie. Okay. So now there is another question. Actually, there is some theorem is there. Okay, you can define something called analytic manifold. Okay, so what is the analytic manifold? You just demand that this on that manifold, you just demand that open subset to diffeomorphic to some open subset of Cn. Okay, so yeah, on any manifold you need to define something coordinate chart, and you demand that open set is homeomorphic to an open subset of Cn. Okay, so let's suppose and let M be a analytic manifold. Okay. So yeah, let us give the full definition. And you also demand. Okay, so let M be a. Okay, so I just topological space. M is called analytic. Sorry, manifold if M is equal to some U alpha and C, and this phi alpha is so I really okay, and phi alpha U alpha and there is some coordinate chart. This phi alpha U alpha is an open subset of Cn. Actually, I have sorry, I am writing vaguely, but you can understand. And third thing is actually this phi alpha phi beta inverse. This is some open set B beta to okay, B beta intersection. Okay, this map, transition map, you really demand that this is an analytic map. Yeah, so okay, this is the definition of analytic manifold. It is known that if G is a Lie group, then there is an analytic structure and the group operations are also analytic. Okay. So yeah, it is a very strong statement that a Lie group has an analytic structure and this multiplication map is analytic and inverse map is also analytic. Okay, next time I will really write this and this is actually comment in Helgason. Okay. But for complex Lie group, I think this is the definition that this the Lie algebra is a complex vector space. That's all. Actually, what I know.
That's correct.
And also one thing actually you will see that the thing is symmetric space. Everything actually Helgason actually defines in from the beginning itself. He defines that it is a analytic manifold because of this thing. Okay. You can see that there is a section after this Lie theory, Lie group, where he has written this. It has written that Lie groups are basically analytic manifolds, and this multiplication map is analytic, and this inverse map is analytic. Okay, so I just want to stop here. Actually, I would have written this definition of this analytic manifold precisely, but I hope you understand. Otherwise, next class you ask me definition of analytic. So let us not worry about this thing, analytic manifold from the thing, and how so some of you want the definition of Lie group, right? Lie group, Lie algebra definition. Is anybody here in the who wants this Lie algebra definition also?
No, you can just recall them briefly next time for the benefit of everyone. Just to
Okay,
make
okay, I will recall that then. Okay, so let me
just
stop here.
yes.
Okay, and another thing is remember that Friday class is 2:30 to 3:30. Okay.
Yeah.
Okay, Munna, so this is what you.
Yeah.
So can you going to share this PDF?
Can
Will
you?
you share this PDF?
Yes, I will share this.
And do you have this any plan for the lecture? Because you have written very precise. But this is too much. I can see. But
Yeah, I will try to cover actually everything. Actually, whatever I will cover, I am thinking that to cover it well. Means